Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Chris Jackson. We're going to be talking about physics of failure modeling and the perception that exists, that it's quite hard to do.
There was a question we got. It was like, and it was very short. It was, why is physics of failure so hard? And I'm like, okay. In my memory of it is that you get a team of grad students that spend a year or 2 years putting together all this cool data and experimentation and understanding the actual growth habits of particular corrosion elements in some exotic strain of steel or something like that. And they come up with, well, you need to know the thickness and the grain size and the grain orientation and the electromagnetic field density, and on and on and on. I'm like, I need 75 pieces of information to figure out whether this capacitor is going to crack or not. How about I just bend it and it cracks, and then I know. And they said, well, we don't have to do testing if we have the right formula that is really good at predicting this stuff based on first principles. How does material move and behave and strain and stress things and yield strengths and all of this other stuff. So we need all of this information. And then I looked at him and said, so what exactly is a modulus? I had no idea. And they said, well, you just need these numbers. Well, what if I don't have those numbers? Well, then you put in, you got to run the experiments to come up with those numbers. And so years later, I ran into a site. It's called WARP, WARP. And it was a database saying, if you're using this kind of steel, here's some papers that describe models for corrosion or strength or whatever it is, that different failure mechanisms. And then they had thousands of papers. And what they did is they showed you the formulas, but they neglected to include any of the constants. So if this beta value was typically a 2, you had to go get the original paper to see that. So you put all the good stuff up on this database, but you didn't add any values to it. And their claim was, well, they didn't want to violate copyright. I was like, well, then why are you doing this? And I went to paper after paper after paper in that database, and one of them had 47 different things you needed to figure out before you could run the calculation.
Yeah.
So I sympathize with the questioner that says, why is it so hard? And that's the way I translate it, is that the difficulty is that you have to learn both the Greek and the Latin alphabet and what all those symbols mean and what they stand for, because it's different. The beta I'm talking about was not a Weibull distribution. It was just happened to be the second variable in that list. And on and on and on. And you have to have a PhD in material science for some of them to even get a clue of what they're talking about. And then on the other end of the spectrum is there's software that makes a zillion assumptions if you don't have the numbers right at hand, and then you get a number out, and it's sort of a black box to me. So I sympathize with why it's so hard.
I think, though, it has a bit of a bad rap, physics of failure, because I think we do physics of failure more often than we realize. And anyone who's plotted data on an Arrhenius plot has, by definition, examined physics of failure or used a physics of failure model.
Well, if they're dealing with a chemical reaction. I've seen way too many people use the Arrhenius equation for anything other than a chemical reaction.
Right. Okay. Yes. I take your point. And that's when they're using the wrong physics of failure model. But when you're genuinely using a physics of failure model, when you genuinely realize, okay, my thing's failing due to a chemical reaction, and they make the link, I can use an Arrhenius plot to conduct accelerated live testing.
Yep.
That's physics of failure modeling right there.
Yep. No, I totally agree.
Another example, and I taught this last night to my course, is I looked at Ford's virtual sensor for its brake pads. And essentially what they came up with is really incredibly clever and simple and smart. Was it understanding how much brake pad material has worn away has been an enduring problem for lots of different scenarios.
Mm-hmm.
And there have been lots of attempted solutions where, for example, there are conductive wires that go through brake pads. And as soon as you wear away a certain amount of material, one of those conductive wires gets taken out. And so you lose that part of conduction. So you can sort of keep track on how much brake pad you have left.
That's cool. I wonder what thermal expansion would do to those wires over time.
But it was just too problematic in terms of being able to get a current to go down to the calipers and have current come back because, as you know,
It's
the
moving. It's
it's just a dirty environment just
yeah,
down there. It's just challenging. It just
yeah,
stuff goes wrong.
yeah.
But what Ford did was essentially say, you know what? We know that distance isn't the best way to measure the age of brake pads. Is we know that the amount of brake pad material that we lose is more analogous to the total amount of energy that the brake pads have dissipated. That's all brake pads do.
Yeah. If you're like a city bus driver and you're just slamming on the brakes every time you come up to a stop, you're got a lot of mass against a small area, and that's going to be a lot of wear versus the one that coasts into it, you know?
Right. So you can't even, so like, even seemingly identical scenarios, i.e. bus with a bus driver, you're going to have different, just in the driving patterns alone, you'll have different rates of brake pad wear.
Yep.
And so what Ford did is they said, we know that the amount of material loss is going to be much more closely linked to the total amount of kinetic energy dissipated. And so they came up with a plan where, of course, vehicles these days can really easily measure how fast the vehicle is going before and after a braking event.
Yep.
And then comes a mass bit. How do they measure the mass? Because, there's payloads and people put loads in the back of the truck. And they had an ingenious way of doing it where every time the driver hit the accelerator, the onboard computers could measure how much energy was being imparted into the vehicle from the engine, and then measure how fast the vehicle was accelerating, and essentially do the math and say, okay, based on the vehicle accelerating this quickly, it must weigh this amount in total.
And they have a good starting point. They know the mass of the vehicle,
Right.
roughly, pretty close, and then they have to just make an adjustment based on the load that it's carrying.
Right.
And yeah,
But it does it every single time.
Yeah, and there's that. Was it one of Newton's laws? The
Plausible
second
mass by
law.
acceleration. Yeah.
Yeah. It was second or third law, something like that. And there's this mass thing in there. I always wondered what that was, and they used it. Cool.
And that meant that what was a very wide bell curve in terms of how long it took for brake pads to wear out when you're looking at it with respect to distance, that bell curve now collapsed around a very central number with teeny tiny deviation each side when you looked at brake pad wear with respect to amount of kinetic energy dissipated, which means that onboard computers can now have a much better idea of how close those brake pads are to wearing out. And it's not just applicable for trucks and vehicles on the road in terms of personal motor vehicles. You got mining sites, you got, commercial trucks.
Aircraft have very expensive braking systems.
Right. And so it becomes very, very useful. And it's not a full-on physics of failure model that people initially jump to when they say, it has 48 different parameters this, and you need to research the strain hardening exponent and the stress intensity factor and blah, 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 blah.
No, you've read one of those papers.
Oh, yeah. I know. But just knowing that if you look at a physics of failure model and just saying, if we could somehow measure the energy dissipated, this would be better.
Yep.
That's physics of failure modeling. That's it. I mean, that's an example.
Well, it's what I think. I'm thinking of the electronics ones that DFR Solutions did. I think they're now part of some other organization, and CALS at University of Maryland. They both have physics of failure models that will look at capacitors and resistors and then electronics of all kinds in the circuit board, and they look at vibration and thermal expansion and contraction, and they must, both models, the last time I looked at them, covered on the order of dozens and dozens of different failure mechanisms, all of which are good things to check. And The downside is it doesn't cover somebody putting a sticky, dirty fingerprint on the middle of the board that causes corrosion, or it doesn't cover everything, which is it's not a slam on physics of failure. It is what it is, and it's way better than doing a parts count prediction by far for the things it covers. And yet, in order to do a circuit board with its 25 different families of parts that are loaded on it and different thickness of the board, you still needed to know what kind of material it was, what kind of how thick the copper is on the inner layers, and it went on and on and on. It the difference between getting the bill of material and getting all of the internal drawings and all the material specifications for all of these different components and materials was daunting. And so over the years, they've tried making that simpler and simpler. If you know the vendor of the circuit board, then they pretty much know what that is, and they can, it's been built into those models. And it does really nice stuff is the way I look at it. It helps us understand if that the one place I really saw it shine is this one company was doing a satellite, and it was in a relatively low orbit. So it was spinning around the Earth really fast. And it went from the sun side to the dark side, like 40 times a day or something like that. And they were worried about the temperature difference, which was about 240 degrees Celsius temperature swing per cycle. And I'm like, geez, I can't even get a accelerated test on Earth to do that. And so they were rightfully worried about that. So we went to, I think it was CALS, or I don't know, one of those models, and they ran it in there, and they were able to put in different strategies in their design and then run it through those models to see which one actually made a difference for them, for the dominant failure mechanisms that they were worried about. And so they didn't need to run a bunch of experiments. They didn't do a bunch of stuff in it. They were able to iterate their design much, much faster. And the last I heard, their satellites were just fine. They worked just fine. But it started with, they were like, we're worried about this thermal cycling, which is step one, and knew what the stress was. And then they went and found those models that allowed them to check that assumption on their design with great detail. And it was sort of like doing finite element analysis, but for an aging of dozens of mechanisms. So it was the right thing to do at the right time, and made a big difference. What I don't see, though, is that it being used on say a consumer product that's, $10. You don't see it being used in those realms very much at all.
Well, I mean, yeah, again, it comes back to what physics of failure is and is not. I mean, is those SN curves that we get in the back of, materials textbooks for fatigue, you could argue that are they physics of failure models? You could argue that they're actually non-parametric models because they're created by thousands of steel specimens being tested in labs to create that SN curve plus 90% confidence regions and things like that.
Yeah. No, I had a mechanical engineer tell me that, it really depends on what's the shape of the metal that you're dealing with and how you grasp it. And, the force, if it's linear, that curve might be just perfectly great, but you put a little twist on it, it doesn't apply.
Right. You got torsional stresses in it as well, but that then you can still, let's just say that it is a physics of failure model. Again, some people would say it's for your perfect scenario where it's just tensile stress, not torsional stress.
Right.
So you have this SN curve derived from thousands upon thousands of samples being tested. And okay, well, that's not one might argue that's non-parametric. You could also argue is physics of failure because you're actually studying a very particular failure mechanism very, very well.
Yep.
And so, but for steels, you have this thing called the endurance limit. And so I do an exercise with the courses I'm on where we use finite element analysis to predict the stress of a door handle being opened cyclically. So, okay, let's work out what that means in terms of time to failure because of fatigue for this 1045 steel, blah, 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 blah. Or we could work out what the endurance limit is, i.e. the stress below which fatigue will never occur for steels, and change the design so we reduce the stress. which one do you want to do?
Yeah.
It's but knowing that there's an endurance limit, I'd argue, is understanding the physics of failure for fatigue.
Yeah,
And
and
so again,
I've run into that argument where it's like just because you've learned calculus, it's the thought process of that's how things happen. It's a way to describe things that occur in the world. It's the area under the curve. So what we got to deal with. I could do the calculus, but by understanding that concept, I can change my design. I can just understanding the concept. And I think that's what you're after with
yeah.
the endurance limit is, well, we know that that's a phenomenon and we get this, it doesn't accumulate damage if we stay well below that. So let's just do that.
But that's physics of failure right there.
Yeah.
That deduction or that a realization that or understanding there's an endurance limit, that's physics of failure. So whether you like it or not, you're doing physics of failure modeling in your head. If nothing else, you don't have 48 different parameters.
Yep.
There you go. That's
Okay.
what it
All
could look
right.
like.
Well, I guess we're doing more of it than we're doing. And
I,
it's if you're going to do the PhD level thesis for every failure mechanism on your system, yeah,
mhm.
then you're off into the deep woods kind of scenario. And I struggle to keep up. What in the world are you talking about? And but it doesn't need to be that far out.
No.
For the satellite one, they really only used a portion of those models, the ones that applied to thermal cycling. They didn't really care about vibration too much, except for they were assuming the flight off the launch pad would be nice and smooth. But I think they figured that out later.
Right.
Um, that the idea is that it's you got to think about the real world and what's actually happening and how does this material change or behave. That very first degradation model I did on it was a polymer system, and up until that point, they always did a straight line, well, a linear model using Arrhenius. They used different thermal chambers, and they would measure the power output of this device that we're using, which would degrade with time at different rates with different temperatures. So they would take a handful of points and stick it in an Arrhenius equation and call it a day. And I had learned early on that you need to actually look at your data. And I noticed that every one of these curves or sets of data had a curve in it. So they never really fit a straight line on the type of plot we're doing. And it's like, there's something else going on here. And long story short is I went to the chemist in our building and said, why would this oxidation process slow down? And he said, oh, well, this polymer, he just knew it. He just said, oh, this polymer, once it starts to oxidize, is sort of like corrosion on copper. It stops further corrosion. He says, it's not like steel, where it just keeps going. It creates a protective layer on it, and it reduces the amount of oxygen that get into the inner layers of this. Oh, okay. There's a physical reason for this phenomena that we've been ignoring for 20 years. And it
That
was
right there is
knowledge that was
physics of
in the
failure.
is right
Yeah.
there. And so we ended up using that model and really shortening the amount of time that we had to run these tests and actually got way better information. And it was anecdotal information from the folks that worked in the field said, yeah, it degrades 10, 15% over the first year or two of use, and then it flattens out. It doesn't get much worse. So I don't know why you're worried about the lifetime of this and that and the other thing. But the design team was kind of isolated from that field information coming back, the anecdotal evidence, and never looked at the data to say, oh, why is this not lining up with the model that we're using? So there must be something else going on. So, geez, I've been doing physics of failure, and I'll put that on my resume.
Absolutely. We do it more than we think. And we pretend it does, we pretend it's not real more than we think. Yeah, as in the design team who's using the wrong model, that's
They
them.
stopped thinking about it. They didn't look at it. It
Exactly.
was just a step in the process. We got to knock it out. And
That's right. And that's why aluminium or aluminum, exactly the same phenomenon where you get that oxide coating when it starts to corrode and it protects it from more oxidation
yeah.
or corrosion. It's just, that. So you don't have to worry about modeling
It might not be the right
corrosion.
phrases. We use it more than we think. We probably need to rephrase that. We use it when we think.
Yeah, actually, that's a good one. It's a good way of saying it. But even when you just say, okay, we prefer to use this polymer because it doesn't break down as quickly under UV light as this one, or
Mm-hmm.
we want to use a ductile material because of this, that, and the other, or that right there is an physics of failure modeling in terms of your judgment calls in your brain, at least, if nothing else.
Yeah.
And it's
And when
quite
it's
often
important,
used.
you go figure it out. You go test it. You go evaluate it. And then once you believe that model and it helps you make decisions, then you just use the model. You don't go to the lab anymore.
Right. But you only need to do it for a certain thing. I mean, like modeling creep, how things slowly deform over time under stress.
Mm-hmm.
That could be very important for the turbine blades in a jet engine. I could see why you'd have a physics of failure model for them
Yep.
because that massive centrifugal forces, and as one blade gets slightly longer than the rest, the end of that blade wears out, which means you have an unbalanced load, which then creates fatigue. But that it's a very simple model or simple failure to understand, even though the metallurgy involved is highly complex and the stresses those turbine blades are exposed to are also extreme, but
Yep.
still it's extraordinarily simple. And that's where you would have a lot of benefit in having a physics of failure model that has been shown to be correct for that steel or that alloy. That model's creep. So you know exactly when that thing is going to start becoming a problem. But you don't do that for every single failure model.
Right. And I think that's where I run into these like for electronics circuit boards is they want to check all the things they can check. And I'm like, yeah, then you need way more information than you really need to just answer the question you have. Think through it first. And who knew? I am going to put that on my resume. User of physics of failure. Um, that might be interesting. Anyway, it
Right.
was an interesting question. It was, yeah. And I agreed with him at first. I'll have to revise my answer and send another comment back to him saying, we actually do it more often. You when you're thinking, you're actually probably using physics of failure type concepts, which be a way to put it. All right, cool. It was a couple of interesting questions lately, and I keep looking for these and various interesting ones. And one I was talking to Kirk the other day about was a question on how do you convince a team that halt is actually a useful thing to do? How do you change the mindset around it type stuff? So that was an interesting question we got. We've been getting a few. So I'm looking for way more questions. We're coming up on our 1,000th episode. So I'm looking for some just doozy questions that we could get in as we round out 1,000 episodes and have to change our naming convention from 3 digits to 4.
Like, how do you spell MTBF?
Yeah. Yeah, don't get me going. But if you're listening to this and wondering about physics of failure and if it's hard or not, hopefully we convinced you that it's, a little bit of thinking about what you're doing, the materials you're using and the options and choices and how it behaves in the real world. That's evidence that you're doing physics of failure. And keep up with that. Do more of that. That's way better than some of the alternatives we have out there. So if you've got a question and you'd like to join the conversation, let us know. Head over to ascendoverliability.com/go/SOR. And Chris and I and the other hosts of the show are available through LinkedIn and our About pages. And we always look forward to your questions and try to get you a reasonable answer. And sometimes after chatting about it, got to update my answer. So that could happen too.
Mm-hmm.
So anyway, I'm going to go think deep thoughts later today with splitting firewood, probably.
Deep thoughts, the only thoughts I have these days. That's the why. Playing a little bit right.
Yeah. Well, anyway, have a good one. Good chatting, Chris. Appreciate it. And we'll see what other questions show up in the near future and we'll get back online.
Always a pleasure, Fred.
All right. Cheers. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.